Hello and welcome to the last video of the semester. So we are a little ahead of schedule for the material that I wanted to cover for this semester. So I want to cover a little bit of extra material that is going to be discussed in Chem 1510 next semester. So it gives you guys a little bit of a head start on some more material that we're going to be covering next semester. So this chapter is going to be talking about and discussing the different gas laws that we as chemists come in contact with. Now, in order for us to discuss these gas laws, we need to remember how gases behave and what some of their special properties are when comparing them to solids and liquids. So one of the major properties that gases have that solids and liquids do not is that the volume of a gas can change significantly with the pressure. So if we think of a balloon, if I have a balloon in my hand, I can compress it down fairly easily by just squishing it. The volume of that balloon changes dramatically by just a little bit of extra pressure pushed onto it. So the pressure and volume are related, and we can see that gases can change dramatically. If I push on a table, the volume of that table does not change. If I push on a liquid, it changes somewhat, but doesn't change to the extent that a gas does. So this is one of those special properties that gases have that solids and liquids do not. If we go on to another one, gas volume significantly changes with temperature. So if I take that same balloon and I cool it down, I throw it into the freezer. If you throw a balloon into a freezer, what's going to happen is the balloon is going to shrink, and it's going to shrink by a large amount. If we do the same thing to a solid or a liquid, like we throw a piece of wood into the freezer, the volume doesn't change significantly. If we throw in a liquid into the fridge and it cools down, the volume doesn't change that significantly. Now with water, if you freeze it, it has special properties just because it's water, so that volume does change, but that's a special property. So think of cooling it down, not necessarily freezing the liquid. So just cooling it down, the volume of that does not change. If it did, if we had a cold glass of water, it would have a smaller volume than if we let it heat up. So that would be a very weird world, a very interesting world, but it would be very weird. So the only phase of matter that actually does that is the gas. If we have a cold balloon and we let it sit out in a hot room, it actually expands. So that's a second property of that gases have, that solids and liquids, not to the extent. They don't have it to that extent. Gases flow freely. This means that if I have an oxygen a grouping of oxygen molecules in their gaseous form at one end of a building, it's going to completely fill up the entire space. That's good for us because if we didn't have it, if the gases didn't work in that way, we would have pockets of air that were breathable, and we would have to be running to these different pockets of air in order to survive. So we know from our everyday life that the gases completely surround us. They flow in all parts of every building. This is good for humans, so we need it to be able to breathe. That's a third property. Gases have relatively low densities. This is also very good. If you're running outside and the air had a very high density, it would be like trying to run through water or trying to run through molasses. But gases don't have that high of a density, so you can freely walk through it. They kind of move out of the gas molecules move out of your way as you're walking around. So they have very low densities. Solids and liquids, very different case. The liquids can have very high densities. Solids are extremely high densities compared to gases. You can't walk through a wall. Okay? Gases form solutions in any proportions. What this means is if I had a bottle, a container of nitrogen gas, and a container of oxygen gas, and I throw them together in a single container, they're going to form a homogeneous mixture. There aren't going to be pockets, most often based on the density, of nitrogen and oxygen. They're going to be freely mixed together. So they're going to be able to form these a solution in any of these proportions. These are the very fundamental properties that we'll be discussing when dealing with these gases. So just want to get your mind thinking again about what gases are. Now, what is pressure? You heard me talk about pressure, and that's me exerting this pressure onto this balloon. Well, there's an actual definition of pressure. Pressure is equal to the force divided by the area. So that balloon has a certain surface area, and the force is me pushing on that balloon. So pressure is actually the act of pushing on a certain surface area. So that's the true definition of what pressure is. We have lots of different units that are associated with pressure, and I'll show you that on the next slide, but this is actually what we talk about when dealing with pressure. So we know the units are going to be of pressure are going to be in force per area. And we know that area is just going to be length squared. Now, force is something we don't quite know yet, so we'll be discussing that as well. You've probably heard about atmospheric pressure. This is the external pressure that you feel from the gases in the Earth's atmosphere. So if you're outside, you have some certain pressure that's pushing on your skin. It's equilibrated to the pressure of the gases inside of your body trying to come out. So we don't have any mismatch of pressures. This is good for us because if the pressure on the outside was less than the pressure inside of our body, like in space, the gases inside of our body would want to leave our body and try and move out to the lower pressure system. So this is why when you see science sci-fi movies, when people are out in space and they get a cut in their spacesuit, you sometimes see them explode. That's because what they're trying to show is the gases inside of the body are trying to expel themselves, and your body's skin is not strong enough to actually withstand that type of pressure difference. So it can also be seen as you go deeper into the ocean, the pressure at very low levels of water is extremely high, and so it would actually crush you. So this atmospheric pressure is just us walking around every day. Our bodies have become acclimated to it, so we have the skin tough enough to withstand the external pressure and to withstand the internal pressure of our gases inside of our body. Atmospheric pressure decreases with altitude. You all know that I'm from Colorado. When I bake, let's say, brownies up in Colorado, it's different. I have to use a different setting on my oven and I have to use a different recipe than when I'm down here in Ohio. It's because our atmospheric pressures are significantly different. We'll do an example in class tomorrow where we actually see this difference in pressure based on the altitude in Columbus versus the altitude in Denver. And that's only 5,280 feet. That's only 1 mile difference in altitude, but the pressure change is significant enough that I can't bake. It took me a long time to learn how to bake again when I was in Ohio versus Colorado. So this pressure, atmospheric pressure, we'll talk about this to some more extent on Tuesday. These are our units of pressures. We have Pascal, atmospheres, millimeters of mercury, torr, pounds per square inch, and bar. Now you've probably heard 2, maybe 3 of these. You've probably heard atmospheres. This is atmospheric pressure. And you probably have heard pounds per square inch. This is the PSI that is in your tires. So we can do some conversions between PSI and atmospheres and see how much atmospheric pressure we have in each of our tires. Now that it's getting a little colder outside, you'll see people pull over to a gas station and start filling up their tires. They do this because since it's colder, the pressure inside and the volume inside of the tires decreases. So they fill it up with more gas, which allows them to have better tire pressure, which allows them to have better gas mileage. So all of this gas law is really fundamental to the way that humans interact with the universe around us. So these are all the definitions. A Pascal is this number. The way we can read this chart is 1 atmosphere is equal to 1.01325 times 10 to the 5th pascals. So we can always relate them back to this 1 atmosphere. That's what this chart is. 1 atmosphere is equal to 760 millimeters of mercury. 1 atmosphere is equal to 760 torr. 1 atmosphere is equal to 14.7 pounds per square inch. So we'll talk about these. Do not worry, you don't have to memorize them. I will give you a table of these on the final. I'll give you probably a short worksheet to work the first 2 gas laws that we're going to cover, and then that'll be the only information that's new that'll be covered on the final. Okay, so we'll be using these units. And don't worry, they'll be very simple gas law problems. I'm not going to try and trick you. This is new material. It's kind of extra material. I still want you guys to be able to know how to work with the units and with the equations that we're going to be discussing.